So you're gearing up for a machine learning interview? Well, if you want to nail the top questions recruiters are actually asking right now, you are in exactly the right place. Welcome to this explainer. Today, we're basically acting as your ultimate recruiter-friendly cheat sheet for sequence-to-sequence models. We're going to break down the exact, confident answers that will make you completely stand out to hiring managers. Watch till the end because we're taking some pretty complex model architectures and turning them into clear, expert-level answers. Here's our game plan for today. First, Seq2Seq basics. Then, encoders versus decoders, the attention mechanism, autoregressive versus masked models, next sentence prediction, and we'll wrap it all up with a rapid-fire review. Let's just dive right in. All right, Section 1, Seq2Seq basics, the foundation. Okay, before we get into the really cutting-edge stuff, you've got to prove you have a rock-solid grasp of the basics, right? Picture this. You're sitting across from a senior engineering manager, and they kick things off with a deceptively simple question. What are sequence-to-sequence, or Seq2Seq models? A huge mistake candidates make here, rambling. Or, just blurting out random models like ChatGPT. You need a crisp, structured answer. Here is your perfect slam-dunk answer. Seq2Seq models are neural network architectures specifically designed to transform one input sequence into a totally different output sequence. And here's the absolute crucial part you have to mention. These sequences do not have to match. The input and the output can have completely different lengths, entirely different meanings, and even use totally different vocabularies. You aren't just mapping things one-to-one. You are transforming them. To really wow the interviewer, you want to immediately back up that definition with real-world applications. Point out that anytime a problem involves mapping one sequence to another, a Seq2Seq model is probably running under the hood. We're talking text summarization, speech recognition, chatbots, and of course, machine translation. Think about it. If your input is the English phrase, how are you, your output might be the French phrase, comment allez-vous. Notice how the lengths and the structures of those two sentences are completely different? That is the exact problem Seq2Seq was built to solve. Moving right along to Section 2, encoders versus decoders, the architecture. To make this whole transformation magic happen, we really need to understand the engine. If they hand you a marker and ask you to draw the architecture on a whiteboard, this is the exact mental model you want to sketch. It's a 5-step pipeline. We start with the input sequence, which flows directly into the encoder. The encoder takes that and compresses the information into a context vector. Then that context vector is handed off to the decoder, which finally generates the output sequence. So it's a step-by-step process. It reads, it compresses, and then it generates. Naturally, the very next thing they're going to ask is, what is the core difference between an encoder and a decoder? Honestly, this is a super common interview question, and mixing these two up, yeah, that's an instant red flag for any recruiter. Notice how crystal clear the separation of their jobs is. The encoder's job is purely understanding. It reads the input sequence step by step and compresses it into a meaningful internal representation, that context vector we just talked about. It extracts the features, but it absolutely does not generate the final output. The decoder, on the flip side, is all about generation. It takes that encoded meaning and produces the output sequence one single token at a time. It actually uses the previously generated tokens to predict the next word until it finally hits an end token. Just remember, the encoder understands, the decoder generates. Next up, Section 3, the attention mechanism solving the bottleneck. But, there was a major historical bottleneck with that basic setup. An interviewer might throw a curveball and ask, why do we even need the attention mechanism? Well, here's the deal. Traditional Seq2Seq models compress the entire input into one single fixed-length context vector. For short sentences, totally fine. But for long sentences, it created a massive bottleneck. Information just got lost and performance tanked. The attention mechanism completely solved this by allowing the decoder to look dynamically at different parts of the input sequence. So instead of one fixed vector, it uses a dynamic, weighted combination of encoder outputs at each specific decoding step. It literally pays attention to what matters most right in that moment. And this exact breakthrough is what paved the way for all the modern transformer architectures we use today. All right, Section 4, autoregressive versus masked models. Now we are definitely getting into advanced territory. How do autoregressive models differ from masked models? If you can answer this clearly, without stumbling, you are going to look incredibly smart and, frankly, highly hireable. Let's break this down really simply. Autoregressive models generate text one token at a time, moving strictly from left to right. They predict the next token based only on the previous tokens, meaning they can't see into the future.
Masked models, however, are trained by randomly masking or hiding tokens inside a sentence, and the model has to predict those missing blanks using bidirectional context. It looks at both the left and the right sides of the missing word. Here's the absolute best intuition to share with your interviewer. An autoaggressive model is like a human typing a sentence from left to right. But a masked model, that's like reading a whole sentence to fill in a blank on a test. So if you only memorize one single thing from this section, make it this soundbite. Autoregressive models are generation-focused. Masked models are understanding-focused. Just drop that line in an interview, and you've perfectly summarized a really complex architectural distinction in 10 words. To firmly connect all this theory to actual industry reality, here is a quick cheat sheet. Masked models are typically encoder-only, used for classification and text understanding, with BERT being the most famous example, of course. Autoregressive models are typically decoder-only, built specifically for text generation, like the entire GPT family. And when you combine them into an encoder-decoder model, you get systems that are absolutely perfect for translation and summarization, like T5 and BART.
Moving on to Section 5, Next Sentence Prediction, or NSP. Let's dive a little deeper into how these specific models are actually trained, because understanding training objectives shows a deep foundational grasp of machine learning, not just a surface-level one. An interviewer might ask you, what is Next Sentence Prediction, or NSP, and why was it introduced? NSP is a pre-training objective most notably used in BERT. Basically, the model is given two sentences, sentence A and sentence B, and it has to predict if B logically follows A. And this is a brilliant way to illustrate how models learn context. For example, if sentence A is I went to the store to buy groceries, and sentence B is I bought milk and bread, the model outputs is next. Makes sense, right? But if sentence B is suddenly Mount Everest is the highest mountain in the world, the model outputs not next. During training, 50% of the time the sentence is real, and 50% of the time it's totally random. This really helps the model understand discourse structure and overall paragraph coherence. But here is a massive pro tip if you really want to impress your interviewer. Mention the limitations. Point out that while NSP was heavily used in the original BERT paper, later research actually found it didn't always significantly improve performance. In fact, models like Roberta removed NSP entirely. They chose to focus solely on masked language modeling and actually achieved better results. Sharing a detail like this shows you actively keep up with practical, up-to-date industry knowledge, not just what's written in old textbooks. And finally, Section 6, Rapid Fire Review Bonus Round. All right, take a breath. You've made it through the heavy architecture. Here is your rapid-fire question. These are often thrown in right at the end of an interview just to test your core definitions. Ready? What is the primary goal difference between an autoencoder and a Seq2Seq model? Here is the punchy, satisfying answer you want to give. The goal of an autoencoder is reconstruction, meaning the input is meant to perfectly equal the output. But the goal of a Seq2Seq model is transformation, meaning the input explicitly does not equal the output. If you nailed that, huge congratulations. You have officially mastered the technical differences that trip up so many candidates. We have covered a massive amount of ground today, from the absolute basics of encoders and decoders, to attention, to the nuanced differences between autoregressive and masked models. But I want to leave you with one final thought. Think about it, if later models like Roberta prove that we could just drop accepted standard training tasks like next sentence prediction and actually get better results, what other accepted AI training rules are just sitting there waiting to be broken by the next big architecture? You want to keep that curiosity alive because that is exactly the kind of mindset top tech companies are desperately looking for. Thank you so much for joining me on this explainer. If this helped you prep, please drop a like, subscribe for more interview deep dives, and comment below on what topic we should cover next. Best of luck on your next interview. You're going to crush it.